How long do you think it would actually take you to go to Mars and come back door to door if this was a real mission with real people and not a movie? Would you say a year, maybe a year and a half, maybe two? The problem is, the moment you try to give one clean number, you run into a wall. Because the trip length is not just distance divided by speed. It depends on where Earth and Mars are in their orbits, which launch window you use, what kind of engines you have, and how long your body can safely stay in deep space. But before we continue, please subscribe to the channel to give your support. Let's continue. You probably expect the answer to sound like a flight time, something like, it's 8 months each way, done. But that's not how mission designers talk. When NASA or any serious agency plans a Mars mission, they don't start with how many months. They start with what year is the launch? What kind of trajectory can we afford in terms of fuel? What kind of surface stay does that force? And how do we fit life support, radiation, and abort options into that? The how long is the result of all those constraints, not a simple input you can choose freely. Here's the first key idea you need to lock in. Mars is not a fixed point with a single distance written next to it. It's a moving target just like Earth is. When people say Mars is about 225 million kilometers from Earth, around 140 million miles, they're talking about a kind of average which is almost useless for an actual mission. The reality is much more extreme. At its best, when Earth and Mars are on the same side of the Sun and lined up relatively well, the distance can drop to around 55 million kilometers, about 34 million miles. At its worst, when they are on opposite sides of the Sun, that distance can climb to roughly 400 million kilometers, about 250 million miles. So the path your spacecraft has to travel is not a fixed road. It changes by a factor of around 7, depending on when you go. This is why we talk so much about alignment and windows. You do not just point at Mars and fire your rocket straight at where it is right now. You leave on a curved path around the Sun, and you need Mars to be at a specific point on its own orbit months later, at the same time you arrive. So your question, how long does it take, is immediately tied to when do you leave, because the right departure date sets your arrival speed, your travel time, and your options to come home. So let's zoom out from the simple idea of travel time and look at the whole mission as a timeline, not just a stopwatch. If you want a number that actually reflects a realistic human mission, you have to add several blocks of time together. First, there is everything that happens near Earth before the interplanetary cruise even begins. In most serious architectures, you are not launching one giant rocket that does everything. You are putting pieces of a Mars ship and its cargo into low Earth orbit or even into an orbit around the Moon. You might need multiple heavy lift launches to get all the modules, fuel, landers, and supplies up there. Then, those pieces need to be docked, checked, and tested. That is not hours, that is weeks to months of preparation while you are already in space but still near home. Next comes the outbound leg, the cruise from Earth's orbit to Mars orbit using a standard efficient transfer. That is typically on the order of 6 to 9 months, so roughly 180 to 270 days. This is where your ship is coasting through deep space, thousands of kilometers from any help, moving around the Sun at tens of kilometers per second. It feels slow only because the distances are huge. In terms of actual speed, it's far beyond any aircraft you've ever seen. Now, here's the part most people do not expect. When you get to Mars, you cannot just turn around and head home whenever you feel like it. Your return path also needs the right alignment between Earth and Mars, and that alignment doesn't magically appear a few weeks after you land. For a common mission type called a conjunction class mission, the usual result is that you are sitting on Mars for something like 450 to 550 days, roughly 1.2 to 1.5 Earth years, before a good return window opens. Only after that long surface stay do you start your trip back, and again, if you use an efficient trajectory and reasonable fuel budgets, the return leg is another 6 to 9 months, similar to the outbound leg. So now stack all of this together in your head, several weeks to a few months for assembly and checkout near Earth, about 7 to 9 months outbound, around 500 days on Mars, and another 7 to 9 months inbound. plus quarantine and recovery when you get back. When you add those numbers, you land in a range of roughly 900 to 1100 days total, door to door. That's about 2.5 to almost 3 years of continuous commitment for the crew. And that's before you even talk about the overall program timeline, because the vehicles and fuel production systems may be heading to Mars years before the astronauts do. At this point, you might be thinking, all right, the reason it takes this long is because we're going slow. So why not just go faster? Why not double the speed and cut the travel time in half? This is where the rocket equation shows up and shuts that idea down for near-term technology. In normal life, if you want to go a bit faster in your car, you press the pedal a bit more. Fuel use goes up, but not insanely. In rocketry, the relationship between the speed change you want and the fuel you need is not gentle, it grows sharply. Every extra bit of speed you want, you have to get by throwing more propellant out the back of the rocket. But that extra propellant makes the vehicle heavier. A heavier vehicle needs even more propellant to reach the same higher speed. And that propellant also weighs something, so you get a loop. More fuel makes the ship heavier, which demands even more fuel, which makes it heavier again. So if you try to cut an 8-month Mars transfer down to 4 months using the same type of engines, your propellant mass can shoot up to the point where your ship is mostly just tanks. That is why mission designers talk in terms of acceptable travel times, not ideal shortest possible times. They are trading travel duration against launch mass, cost, and risk. Shaving a few weeks might be reasonable. Shaving several months tends to explode the mass and the complexity. And that also feeds back into safety. Faster trajectories usually mean higher arrival speeds at Mars, more intense heating during entry, and less flexibility to abort or change plans if something fails mid-mission. So already, you can see the shape of the answer forming. If we stick to chemical propulsion, the kind of engines we actually have and know how to use at scale, and we pick sensible, efficient trajectories that we can launch with heavy rockets, we keep landing near the same overall answer. A round-trip human-Mars mission with a long surface stay is likely to be around 2.5 to 3 years, not a quick 1-year sprint. By the end of this whole breakdown, I want you to be able to say something very specific, not just a few years, but something like, for a chemically propelled conjunction-class mission in the 2030s, you might see around 7 to 9 months outbound, roughly 500 days on Mars, and 7 to 9 months on the way back. And you'll know exactly which physical limits force those numbers. But if the duration depends this much on how Earth and Mars move and line up, then the next thing we have to ask is, what are those orbits really doing to us? And why do they trap us into these rare launch windows that are spaced more than 2 years apart? So what are these orbits actually doing to you? Why do they force you into this weird pattern where you can only leave every couple of years? And why does that simple fact stretch your Mars trip into years instead of months? Start with something very basic. Earth and Mars are both going around the sun all the time. Earth does one lap in about 365 days. Mars takes about 687 days, almost 2 Earth years. That means your home planet and your target are not sitting still waiting for you. They are both racing around the sun, and you are trying to jump from one moving track to another, while both tracks are spinning under you. Earth is moving around the sun at roughly 30 kilometers every second, around 67,000 miles per hour. Mars is moving at roughly 24 kilometers every second, around 54,000 miles per hour. So even when you are just coasting between planets, both your departure point and your destination are sliding along their orbits at insane speeds. If you leave at the wrong time, by the time you get out to where Mars's orbit is, Mars itself has already moved somewhere else. Here's the key thing. The important clock is not just how long does Earth take to orbit or how long does Mars take to orbit. The important clock is how long until their geometry lines up in a way that gives you a reasonably efficient path from one to the other. That special interval is called the synodic period. You can think of it like this. If you watch the angle between Earth and Mars from the sun's point of view, how long would it take for that angle to come back to the same useful value again? For Earth and Mars, that reset time is about 26 months, a little over 2 years. That's the gap between good launch opportunities. Not because rockets are lazy, but because the planets need that much time to get back into a good pattern for a low energy transfer. So when people say the next Earth-Mars window opens in year X, what they really mean is the orbits have finally rotated into another friendly lineup. Now here's where the trap shows up. If you try to launch outside that window, even by a few weeks in the wrong direction, you can absolutely still get to Mars in theory, but your fuel budget and your arrival conditions get a lot worse. You might need much higher departure speed, more deep space maneuvering, and you often end up with a bad arrival angle. All of that means more propellant, more mass, more heating, more risk. You either pay that huge penalty, or you accept that you missed the bus and wait roughly another 26 months for the next good bus. So distance itself, the raw number of kilometers, is not your main enemy. What really controls you is alignment. When people throw out a single average distance to Mars as if that tells you how long the trip takes, they're skipping the most important part. The only thing that really matters is, can you leave on a path where your curved trajectory around the sun intersects where Mars will be when you get there, not where it is today. So mission design is less about how fast can we go and more about when can we leave so that our efficient path actually hits the target. Imagine your spacecraft's path as an elongated oval around the sun. That oval touches Earth's orbit at one side and Mars's orbit at the other. Your job is to choose a departure date so that when you slide along that oval, Mars is arriving at the same point on its own orbit. That is why the calendar matters so much. You're not just choosing speed, you're choosing geometry. And if the geometry is bad, your speed hardly matters. You are either too early, too late, or way off in space. Now, once you accept that launch windows are this quantized, this every 26 months thing, there are still different ways to use them, and those choices change the answer to how long is the mission by many months. One big split is between what we call conjunction class missions and opposition class missions. They are two different strategies for juggling travel time, surface time, and energy. In a conjunction class mission, which is what most near-term human studies prefer, you do this. You launch from Earth during a good alignment, you follow a relatively efficient path, and arrive at Mars after something like 6 to 9 months. Then you stay on Mars for a long time, on the order of 450 to 550 days, and you wait for the next favorable alignment that lets you come home without crazy fuel demands. That gives you a longer total mission, but each leg of the trip is relatively low energy, and you maximize the amount of time you can actually do useful work on the surface. Opposition class missions flip the priorities. These try to reduce the time you sit on Mars by leaving again relatively quickly, before the classic long stay point. The idea is to cut the surface time and sometimes the total mission duration, but you pay for it in other ways. You usually need more energetic trajectories, sometimes including swing-bys of the Sun or Venus. You may spend more total time in deep space, farther from both planets. You face higher radiation exposure outside any atmosphere, and you have worse abort options if something goes wrong midway. So when you hear someone say, you can design a Mars mission that's shorter than 3 years, what they usually mean is, if you are willing to pay higher energy costs, accept more time away from any planetary protection, and accept fewer safe exit ramps, you can tweak the numbers. But those choices don't magically break the 26-month geometry, they just use different parts of it, and they move risk and stress around between the surface phases and the cruise phases. Here's the part that really surprises people. Your return time is basically decided before you leave Earth. On launch day, you are not just committing to a departure date, you are almost locking in your return window too, because the orbital dance is predictable. If you leave during a certain Earth-Mars alignment, then for an efficient mission architecture, we already know roughly when the next good alignment for coming back will happen. That's the one that sets your surface day and your total mission length. So when mission planners pick a launch year, they're effectively choosing the whole calendar. They know if we leave in this month, we arrive at Mars in this month. Our good return window opens around this later month, and we reach Earth again around this final month. And that span could easily be 2 to 3 years long, just from orbital mechanics, long before you talk about contingencies, delays, or extended stays. You're signing up on day one for a future where your life is scheduled down to the month for several years by the positions of two planets you cannot slow down or speed up. This is why the question, how long does it take to go to Mars and come back, cannot be answered honestly without talking about orbits and windows. Your ship does not leave a fixed starting line toward a fixed finish line. It is surfing between two moving launch pads that only line up nicely every 26 months or so. And the way you choose to use that rare alignment decides whether your mission is a safer, slower conjunction-class marathon or a more stressful, high-energy opposition-class sprint with worse safety margins. Now that you know the windows themselves are the cage, the next step is to look at the actual path you fly between those windows, because even when the alignment is perfect, you still have to pick the shape of your trajectory, how fast you leave, how much fuel you burn, and how many months you're willing to spend in deep space for each leg. So what does that standard highway to Mars actually look like, and why does it so often come out to something like 6 to 9 months one way? If the orbits are trapping you into rare launch windows, what path are you actually taking once you finally leave Earth? Is it some crazy spiral? Is it a straight line? Or is there a standard default route that almost every serious mission ends up using because physics keeps pushing you back to it? The basic answer is yes, there is a standard play, and it's called a Hohmann transfer. Think of it like this. You start in a nearly circular orbit around the Sun at Earth's distance. Then you do a burn that stretches that circle into an ellipse, an oval, that just touches Earth's orbit at the start and Mars's orbit at the far end. You ride that ellipse until you reach the point where it meets Mars's orbit, and if your timing is right, Mars is there when you arrive. That's the classic efficient highway from Earth to Mars. Why is this path such a big deal? Because among all the simple two-burn solutions, one to leave Earth's orbit and one to arrive at Mars's orbit, this one uses the least total change in speed, the least push from your engines. And for chemical rockets, that quantity is the real currency. The less speed change you need, the less propellant you have to carry, and the smaller and cheaper your mission can be. So how long does that elliptical trip actually take? Here's where we do a bit of broad strokes math in plain language. Any orbit, even an elliptical one, has a period, a time it would take to go all the way around once. The Hohmann transfer only uses half of that oval, from Earth's side to Mars' side, so your transfer time is roughly half of that orbital period. For Earth-Mars, when you work through the standard calculations, you end up with a transfer time of around 250 to 300 days. That's about 8 to 10 months. That is the clean, idealized number. But now add all the real-world factors. You might tweak the path slightly to hit a specific landing site. You might launch with a slightly different speed depending on your rocket. You might adjust the trajectory for safety or communication reasons. Once you fold those in, mission designs usually talk about something like 210 to 270 days, so roughly 7 to 9 months, as the realistic one-way cruise time on a Hohmann-like route. That is the baseline most people quote when they say it takes about 6 to 9 months to get to Mars. They are really talking about this efficient half ellipse aligned with a good launch window. But if the time sounds long and the path sounds gentle, that can trick you into thinking the ship is moving slowly. So let's look at the actual speeds involved. When you leave Earth for a Mars transfer, your spacecraft has to escape Earth's gravity well and end up in a new path around the Sun. That typically means leaving low Earth orbit with something like 11 to 12 kilometers per second relative to Earth. That's around 25,000 to 27,000 miles per hour. Once you're out in heliocentric space, your speed relative to the Sun is on the order of tens of kilometers per second, depending on the exact geometry. To compare, a typical jet airliner cruises at maybe 0.25 kilometers per second, around 560 miles per hour. So your Mars ship is moving roughly 100 times faster than a long-haul passenger plane. From your point of view inside the spacecraft, it doesn't feel like that. There's no air rushing past, no engine roar, just a constant, quiet freefall. But the numbers are brutal. You are covering millions of kilometers week after week. It still takes months only because the distance you have to cover is so large, tens to hundreds of millions of kilometers between orbits. So if the ship is going that fast, why do we still call this the slow option? Why don't mission planners push for more aggressive paths? The answer is a single idea you have to keep in your head for the rest of this topic. Delta V is king. Delta V just means how much total speed change your mission needs, summed over all the burns. And for chemical rockets, every extra unit of delta V costs you heavily in propellant mass. Once you choose this Hohmann-style trajectory, you have minimized that total speed change for a simple two-burn transfer. If you try to arrive sooner by leaving faster or curving your path differently, you need more delta V, more push. That means more fuel, and that fuel has mass, and that mass has to be lifted out of Earth's gravity first. A 1 kilometer per second increase in required delta V does not sound like much when you say it casually, but in mass terms, it can mean your spacecraft has to carry many tens of % more propellant, sometimes turning a barely launchable mission into an impossible one. This is why calling it slow is misleading. You are moving extremely fast, but you are choosing a path that keeps your engine use and your fuel needs under control. And that choice drives every other part of the architecture: ship size, launch vehicle, cost, risk, and in the end, mission duration. If you stay close to a Hohmann transfer, you are automatically living in that 6 to 9 month one-way range. If this still feels a bit abstract, look at what we have already done with robots. NASA's Mars Science Laboratory mission, which carried the Curiosity rover, left Earth in late 2011 and reached Mars in August 2012. The cruise took around 253 days. That's a bit over 8 months. Perseverance, launched in 2020, took roughly 203 days between Earth departure and Mars landing, just under 7 months. These are different missions, different rockets, and different exact trajectories, but they are both clearly in that 7 to 8 band that the Hohmann logic predicts. These were unmanned missions with no life support, no crew quarters, no return ship strapped on. And even then, when mission teams optimized trajectories for fuel, arrival conditions, and launch windows, they still landed in that familiar 7 to 8 month band. That should tell you something important. Even with perfect robotic discipline and no human comfort requirements, the physics of efficient transfers pins you at around 7 to 9 months one way in most reasonable cases. So when you hear Hohmann transfer, you should translate that in your head to the standard low-energy route that sets the basic travel timescale for early human Mars missions. As long as we rely on chemical propulsion and sane launch masses, we are almost guaranteed to live in that months-long regime, not weeks. And because your round trip also has to respect launch windows and similar paths on the way back, that single choice cascades into the total mission clock we talked about earlier. Now that you have a feel for the standard highway, the next question is, what happens when you add up not just this cruise time, but all the enforced weight on Mars and all the overhead around Earth? How do these individual pieces stack into that brutal, almost 3-year answer for a realistic there and back mission? So when you stop looking at just the cruise time and you actually add everything up, what does the full clock for a real human Mars mission look like? Are we really stuck talking about years of your life, not months? If you follow the most realistic near-term plan, a conjunction-class mission with chemical rockets, the answer is yes. Take the main spine of the mission first. Forget all the extra details for a moment and just lay down the 3 big chunks you cannot escape: outbound cruise, surface stay, return cruise. With Hohmann-style transfers and sensible fuel budgets, your outbound leg is roughly 7 to 9 months. So let's say about 210 to 270 days. Then, because of the orbital alignment we talked about, you do not turn around right away. You wait on Mars for about 500 days, roughly 1.4 Earth years. Then when the next good window opens, you leave on another 7 to 9 month trek back to Earth. Add those three numbers, you're at roughly 900 to 1100 days. That is about 2.5 to 3 years. And that is just the core mission. No fancy extras, no drama. That is the quiet, boring, nominal success path. For a lot of architecture studies, that 2.5 to 3 year span shows up over and over. Not because people like it, but because the combination of orbits, fuel limits, and human safety keeps pushing you into that zone. The obvious question you probably have now is, why not cut out the long wait on Mars? Why not do something more like an Apollo mission? Land, spend a short time on the surface, leave again, and be back home much sooner. This is where orbital mechanics gives you a hard no. You can land quickly, but you cannot leave efficiently whenever you choose. The problem is simple but brutal. When you arrive at Mars after your 7 to 9 month cruise, Earth and Mars are in one particular configuration around the Sun. To get a low energy path back, you need them to be in a different configuration, and that takes time. If you try to depart Mars too early, before the geometry is favorable, you get two bad options. You either aim for an early return and accept a weird high-energy trajectory that burns much more propellant and likely gives you harsh entry conditions at Earth, or you end up on a path that keeps you in deep space for longer, farther from both planets, which is worse for radiation and abort options. So there is a trade you cannot avoid. Either you pay in fuel and your rocket and mission mass go out of control, or you pay in time and you accept a long surface stay. Almost every serious human mission concept that uses chemical propulsion and respects realistic launch mass limits chooses to pay in time, not fuel. That is why the long layover is not a luxury. It's basically forced by the physics of the orbits. Now, what is really going on with that 500-day surface stay number you keep hearing? Why that scale? Not 50, not 150. The reason is that in many conjunction class profiles, you arrive near one favorable Earth-Mars alignment, and you depart Mars near the next favorable Mars-Earth alignment. Those two good windows are spaced by something like 450 to 550 days, depending on the exact launch year and trajectory. That is why the stay time clusters around that value. It's literally the gap between one good phase angle and the next. From a mission design point of view, that has a weird upside. If you're going to spend that long waiting anyway, you can actually do serious work. A 500-day window on the surface gives you time to deploy and expand habitats, test local life support, drive rovers far from the landing site, drill deep into the ground, run long-term experiments, and importantly, prepare for the return, including checking and fueling the ascent vehicle. If you're doing ISRU, making fuel from Martian resources, that long stay also gives you margin to produce, store, and verify the propellant. This is why people say the mission feels long. You are not just flying, you are living on another planet for more than a year, under 0.38 G, with a thin atmosphere, dust everywhere, and no quick evacuation path. Every system has to work not just for a few weeks, but for hundreds of days, and you carry all of that risk on top of the long cruises before and after. Now, layer in the parts of the timeline that are easy to forget when you casually say 3 years. Before you ever start the interplanetary leg, you need time on the Earth side. You are launching large masses into low Earth orbit, maybe into a staging orbit around the Moon or in high Earth orbit. You could easily spend weeks assembling your Mars transfer vehicle, docking modules, moving fuel around, and running full-up tests of life support and propulsion. No one is going to light the big departure burn until those systems have been checked in space, not just on the ground. There's also likely to be time built into cislunar or high Earth orbit for crew adaptation and checkout. The crew might launch separately in a crew capsule, rendezvous with the Mars ship, and spend a period verifying that all the systems they will depend on for years are behaving correctly. If something looks wrong at this stage, it is far better to find it while Earth is still one burn away, instead of halfway to Mars. So mission planners will not rush this phase just to shave a week off the total calendar. On the back end of the mission, when you finally get home after that second 7 to 9 month cruise, you do not just land, high five, and go back to everyday life. After years in microgravity and partial gravity, the crew will need medical checks, rehabilitation, and likely some level of quarantine, both to protect Earth from any unknown contamination and to protect the crew from Earth's germs while their immune systems are still adapting. There will also be debriefings, data dumps, post-flight inspections of hardware. All of that is time, days to weeks, that belongs to the mission, even if it is after re-entry. So when space agencies talk to the public, it's much simpler and more honest to round this whole structure into one statement. Something like, going to Mars and coming back is roughly a 3-year commitment. That captures the outbound leg, the 500-day surface stay, the return leg, and the Earth-side overhead, without burying people in a wall of individual numbers and contingencies. Inside the planning documents, you'll see more detailed ranges, like 900 to 1,100 days, but around 3 years is the right scale to keep in your head. To get a gut sense of what that means for a human being, compare it to things you already understand. 3 years is longer than most people spend getting a basic college degree if you only count active time on campus. It's about the length of a full military tour for many roles. It's longer than many people stay in a single job. From your point of view as a crew member, you are not taking a trip, you are entering a multi-year phase of your life where everything is defined by one mission, one spacecraft, one small group of people, and about 1 to 2 billion kilometers of total travel. Roughly 600 million to 1.2 billion miles when you add both legs and all the orbital motion. And remember, that 3-year scale is not the extreme case. That is the reasonable, we're trying to be safe and efficient case. Once you start adding margins for delays, backup plans, and possible extended stays if something slips, planners have to assume things could stretch even further, which makes every system, from food storage to crew psychology, much harder to design. Longer missions mean more mass for consumables, more spare parts, more redundancy, and more failure modes to think about. So if 3 years is what you get when you play it safe with today's kind of engines and trajectories, the obvious next question is, what happens if we refuse to accept that? If we say, no, that is too long, we want to cut the travel time sharply and get to Mars in 3 or 4 months instead of almost a year, and what nasty costs show up when you actually try to design those high-energy, fast missions? If the normal Mars route already takes 7 to 9 months one way, the obvious question is, can we just brute force it? Can we pour in more energy and get there in 3 or 4 months instead of almost a year? The short answer is yes, on paper, if you are willing to pay a big price. You can design trajectories that reach Mars in something like 90 to 120 days instead of 210 to 270. You leave Earth harder, you bend your path more aggressively, and you arrive at Mars faster, so your cruise time drops. That sounds great until you look at what it does to fuel, mass, heating, and safety. Think about what you are asking the ship to do. Instead of taking the most efficient half ellipse between Earth's orbit and Mars's orbit, the Hohmann transfer, you are asking for a steeper trajectory. You leave Earth with higher speed relative to the Sun, so you reach Mars's orbit sooner. That extra speed doesn't come for free. Every additional kilometer per second of speed change you want has to be provided by propellant, and that propellant has to be lifted out of Earth's gravity first. Here's where the rocket math kicks you in the teeth. There's a standard relation that links 4 things: how much total speed change you want, how efficient your engine is, how strong gravity is, and what your mass ratio is. That mass ratio is just how heavy the rocket is at the start, full of fuel, compared to how heavy it is when the fuel is burned. The ugly part is that the way this relation works is not linear. It uses a logarithm, which basically means if you push for more and more speed, your required fuel mass doesn't climb gently, it surges. Even with a very good chemical engine, something like a hydrogen-oxygen engine with a specific impulse around 450 seconds, going from a roughly 6-month style trajectory to a 3-month style trajectory can blow up your fuel needs. You might think, have the time, maybe double the fuel. But the real answer can be several times more fuel. That pushes your mass ratio up, which means your rocket at launch is mostly propellant with a relatively tiny fraction left over for structure, engines, life support, and crew. And remember, all of that extra propellant has to be launched out of Earth's gravity well. Just getting a kilogram into low Earth orbit takes around 9 to 10 kilometers per second of total speed change from the surface. If your Mars ship now needs much more propellant in orbit, you need more and bigger launchers, or more launches, or more in-orbit refueling. Everything scales badly. The more you try to cheat the clock, the more your entire architecture starts to look like a giant fuel-moving operation with a small human payload hidden inside. But fuel mass is only one side of the problem. The other is what happens when you arrive at Mars with that extra speed still in your pocket. If you choose a fast trajectory and get there in 3 or 4 months instead of 7 or 8, your spacecraft is carrying more kinetic energy relative to Mars. You have to get rid of that energy before you can land or even settle into orbit. And there are only two broad options. You burn fuel to slow down, or you slam into the atmosphere harder and let it do the braking. For Mars, arrival speeds on a fast trajectory can easily exceed 7 to 8 kilometers per second relative to the atmosphere. That is around 15,000 to 18,000 miles per hour. Hitting a thin atmosphere at those speeds drives heating and G-loads sharply upward. Your heat shield has to survive higher temperatures and more total energy. Your structure has to endure stronger deceleration forces. And your landing system has to manage all of that while still delivering a human-rated touchdown. You have traded some months of relatively calm cruise for a much more aggressive, more unforgiving entry, descent, and landing phase. If you say, fine, I don't want such a violent atmospheric entry, I'll just burn more fuel to slow down before I hit the air, you are right back where we started. More delta V, more propellant, higher mass ratio, and a bigger, more expensive vehicle. Whichever way you turn, the cost of going fast shows up somewhere, either in fuel tanks or in your thermal protection system and structural margins. There's another problem that does not show up in the simple time numbers, and that is abort options. On a Hohmann-like trajectory, your energy relative to both planets is lower. Your path is closer to the most efficient curve between their orbits. That still doesn't give you Apollo-style turn around and come home in days capability, but it gives you more reasonable options to adjust the mission mid-flight. You can sometimes do a swing by or adjust to a different arrival date without completely wrecking your fuel budget. On a very fast trajectory, your spacecraft is in a higher energy orbit around the sun, which means that changing course costs more. If something serious fails after you have committed to that aggressive burn, your options to turn back to Earth or divert to a safer path are much worse. Any big correction needs a lot of fuel, and because you designed your system tightly around the fast transfer, you do not have that fuel sitting there as a margin. So your ability to survive surprises drops as your cruise time drops. Compare that to Apollo for a second. On a moon mission, if something went wrong on the way out, you were only a few days from Earth, and the energy level of the orbit was low enough that you could do a free return or a relatively easy course change. With Mars, even on a slow transfer, you are months away, and your speed around the sun is huge. On an ultra-fast transfer, you are in an even more extreme energy situation. So just come back is not a real option unless you designed for ridiculous fuel reserves, which almost no practical mission can afford. So, given all of this, what should you expect for the first human missions? Are we going to see 90-day Mars trips right away? The realistic answer is no. Early crewed missions are almost certainly going to favor reliability and safety over speed. Mission planners will want trajectories that are well understood, low enough in energy that aborts and corrections are at least somewhat possible, and gentle enough on entry and landing that we are not operating right at the edge of what our heat shields and structures can survive. That points straight back to Hohmann-like trajectories, or slightly tweaked versions of them, not ultra-fast racing trajectories. You might see some modest shortening of cruise times if we bring in better propulsion, but not a collapse from 7 to 9 months down to 1 month. As long as chemical rockets are the main driver for crewed missions, and we're working with realistic launch masses, the round-trip mission duration stays in that 2 to 3 year range, even if we shave a little off each leg. In other words, you cannot rescue your schedule just by saying, we'll go faster. The cost curve is too steep, and the safety penalties are too severe. If you really want to change the mission clock in a big way, you have to change something more fundamental than the trajectory. You have to change the engines themselves. So the next question is, what happens to the timeline if we stop relying only on chemical rockets and bring in nuclear or electric propulsion? Can those new engines actually bend the clock in our favor without making the fuel and risk situation unmanageable? If going faster with the same kind of rocket blows up your fuel needs, the next logical question is, can you just change the rocket itself? Can you switch to a different kind of engine that bends the timeline without turning the whole ship into one giant fuel tank? Start with where we are right now. Chemical propulsion. This is the workhorse, the thing we actually know how to build at huge scale. Your big, heavy lift rockets, the ones that put space stations, probes, and maybe one day Mars hardware into orbit, all use chemical reactions, burning fuel and oxidizer together. Typical chemical engines have a specific impulse somewhere around 300 to 450 seconds. You can think of that as a measure of efficiency, how much push you get per kilogram of propellant. The higher the number, the better. The good news with chemical engines is thrust. They can produce enormous force, enough to lift thousands of tons off the launch pad and push big payloads into low Earth orbit. For leaving Earth's gravity well, this is still the only realistic option we have. That's why even advanced Mars mission designs usually keep chemical rockets for launch and often for major burns. The bad news is that their efficiency is limited, with that 300 to 450 second range. Once you run the rocket math, you keep landing at those 6 to 9 month one-way Hohmann-like transfers if you want a reasonable fuel mass. You can tweak around the edges, but you do not get a huge breakthrough. So what if you take a step up in efficiency? That's where nuclear thermal propulsion comes in. Instead of burning chemical fuel and oxidizer, you use a nuclear reactor to heat a propellant, usually hydrogen, to very high temperatures. Then you shoot that hot hydrogen out the back as exhaust. Because the exhaust is much hotter and lighter, it leaves the engine faster, which means you get more impulse per kilogram of propellant. In simple terms, you get more kick out of the same mass of fuel. Nuclear thermal engines could, in theory, reach specific impulses in the range of 800 to 900 seconds, roughly double the efficiency of the best chemical engines we have today. That is a big deal. When you plug that into the same rocket relations, the mass ratio you need for a given total speed change drops. Or put the other way around, for the same mass ratio, you can get more delta V, more useful speed change. That is exactly what you want if you are trying to shorten transit times without exploding the ship's mass. With nuclear thermal, you could realistically start talking about cutting a typical Earth-Mars transfer from around 7 to 9 months down to something more like 3 to 4 months, maybe around 90 to 120 days, and still keep the propellant mass in a manageable range. You're still not at few weeks territory, but you have made a significant dent in cruise time, and that directly cuts radiation exposure in deep space and the duration of microgravity on each leg, which is a big win for crew health. But nuclear thermal is not magic. It comes with its own problems. You're flying a nuclear reactor in space. You have to deal with shielding, safety protocols, and the engineering challenges of running a very hot reactor for long burns, throttling it, and making sure it does not become a failure point you cannot fix halfway to Mars. Still, as a near to midterm option, it's one of the few realistic ways to actually change the Mars travel clock in a serious way. On the other end of the spectrum, you have electric propulsion, ion engines, and Hall effect thrusters. These are already flying on robotic missions, and they're extremely efficient in terms of specific impulse. Numbers like 2,000 to 3,000 seconds or even more are possible. That means you can get a huge amount of total speed change out of a small amount of propellant, which sounds perfect until you look at the catch. They have tiny thrust. The push is very gentle. An electric thruster can run for months or years, slowly adding velocity, which is excellent for cargo. You can launch a robotic spacecraft, put it on electric propulsion, and let it spiral outward, changing its orbit bit by bit. You pay in mission time, but you save enormous amounts of propellant mass. That's why deep space probes love these systems. But for crew, slow burn becomes a problem. If you accelerate and decelerate too slowly, your total trip time might not actually drop, and your spacecraft might spend more time in deep space at low thrust, which is exactly what you want to avoid for humans. So purely electric propulsion for a crewed Mars mission with current technology is hard to justify. You would either need huge power sources like very large solar arrays or nuclear space power plants to produce enough thrust to matter, or you accept that your trajectory is going to be very long, which defeats the purpose. Electric propulsion shines for cargo, not people, at least in the near term. This is where hybrid strategies start to look smart. If different engines have different strengths, why not use each where it makes sense? One common idea is send the heavy stuff first using high-efficiency, low-thrust electric propulsion. That includes cargo, habitat modules, spare parts, maybe even parts of the return vehicle. They take the slow spiral out from Earth's orbit to Mars' orbit, maybe over a year or more. But that is fine. No one is on board. Then, when you're ready to send humans, you use chemical or nuclear thermal propulsion for the crew vehicle. Give them a higher thrust, shorter duration transfer, minimizing the time they spend exposed to deep space. A still manageable propellant mass, you are still not at few weeks territory, but you have made a significant dent in cruise time, and that directly cuts radiation exposure in deep space and the duration of microgravity on each leg, which is a big win for crew health. But beyond that, you enter the frontier, where people talk about nuclear electric propulsion, fusion-based drives, or even more exotic concepts. Nuclear electric is like combining a nuclear reactor with electric thrusters. The reactor provides steady, high power. The electric engines use that power to accelerate propellant very efficiently over long periods. That could, in theory, give you both high specific impulse and more useful thrust than today's solar-powered ion drives. Fusion concepts go even further, aiming for very high exhaust velocities and very high power densities if they ever work at scale. On paper, these advanced systems could push one-way Mars transit times down to several weeks or a couple of months, without the insane fuel penalties that chemical rockets would suffer at those speeds. That would be a real timeline shift. But right now, all of that is still speculative for human missions. We don't have flight-proven, human-rated nuclear electric ships, and we definitely don't have operational fusion drives in space. These live in research papers, lab experiments, and long-term roadmaps, not in launch manifests. So for a real mission framing, anything you could actually put people on in the coming decades is still likely to be either chemical only or chemical plus nuclear thermal, with electric propulsion reserved for cargo. Those setups can bend the Mars clock, maybe pushing one-way times from 7 to 9 months down to 3 to 6 months, depending on how aggressive you are. But they don't delete the core problem. For any rocket that throws mass out the back for thrust, you are still chained to the same basic relation between speed change and fuel mass, and that relation is what really limits how fast and how light you can go. Which brings us to the deeper issue hiding under every engine in this story. Chemical, nuclear, electric, whatever you pick, why does the fuel requirement explode so fast when you push for more speed? What is it about that one equation that makes just go faster such an expensive demand in spaceflight? If changing engines only helps so much, what is the deeper rule that keeps smashing every shortcut you try to invent? Why does just go faster always come back as add a ridiculous amount of fuel? It all comes down to one relationship, the rocket equation. You don't need the math symbols, just the logic. It says this: the total change in speed your rocket can give you, what engineers call delta V, depends on three things: how efficient your engine is, how strong gravity is at your reference point, and how big the ratio is between your fully fueled mass and your empty mass. That last piece, the mass ratio, is the killer, because it means if your engine efficiency stays the same, the only way to get more delta V is to make your starting mass much bigger than your final mass. In plain language, you stack on more propellant. Here's the nasty loop. You say, I want a higher delta V, so I add more propellant. That makes the rocket heavier at launch. A heavier rocket needs even more propellant to reach the same higher speed. That propellant also weighs something, so you are in a feedback cycle. The more speed you demand, the bigger your fuel fraction gets, and the smaller the slice that is left for the actual spacecraft: structure, engines, life support, and crew. Let's give that some numbers so it feels real. Imagine a pretty good chemical engine, something in the ballpark of 450 seconds specific impulse. That's a high-performance hydrogen-oxygen engine. Now, say you design one stage of your mission to need a moderate delta V, maybe around 3.6 kilometers per second. In many designs, that might leave you with a vehicle where around 60% of the total launch mass is propellant, and the remaining 40% is everything else: tanks, engines, structure, payload. Now push that required delta V up to something like 6 kilometers per second. Not double, but a significant bump. Suddenly, that same engine efficiency demands a much higher mass ratio. In practice, your propellant fraction can shoot up into the 80 to 90% range. So now, out of every 100 tons on the pad, you might only have 10 to 20 tons left for all the hardware and payload. The rest is just fuel. Your spacecraft has become a mostly empty shell sitting on top of a giant tank. And remember, this is not even counting the delta V you already burned just to get into low Earth orbit. That's the next brutal piece. Earth's gravity well is the first major hurdle in any Mars plan. To reach a stable low orbit around Earth, including losses to atmospheric drag and gravity, you need on the order of 9.3 to 9.8 kilometers per second of total delta V from the surface. That translates into an orbital speed of roughly 7.8 kilometers per second, about 17,500 miles per hour sideways, and you have to maintain that speed just to stay up there. That means every single kilogram of propellant you plan to use later for your Mars transfer, your Mars orbit insertion, or your return has to be lifted up through that initial 9+ kilometers per second of delta V first. You don't get to magically start from orbit with a full tank at no cost. So when you say, let's add more delta V for a faster trip, you're not just adding fuel to the Mars phase. You're adding to the burden of your launch system as well. The whole stack grows. To cope with this, engineers do two main things. They stage and they assemble in orbit. Staging is the idea of stacking multiple rockets on top of each other. When the bottom stage burns its fuel, you drop the empty tanks and engines, so you're not dragging dead mass all the way to orbit or beyond. That makes the mass ratios for each stage more manageable. But every stage you add is more complexity, more systems that can fail, more cost, and more design work. In-orbit assembly is the other trick. Instead of trying to launch one monolithic Mars ship, you launch pieces: fuel tanks, propulsion modules, habitats, cargo sections on separate rockets. Then you dock them in low Earth orbit or higher. You might even refuel from separate tanker flights. That helps you build a larger interplanetary vehicle than any single rocket could lift. But it also raises the number of launches, rendezvous operations, and dockings you have to get right. Each of those is a risk factor, and all of that effort is often just to gain enough delta V to shave a couple of months off a 6 to 9 month transfer. This is why people who actually design missions live inside spreadsheets and trajectory simulators, not wishful one-liners. When someone asks, could we get to Mars in 30 days? The response is not a yes or no pulled from the air. It's a detailed mass budget, layer by layer. They plug in the desired delta V, the engine efficiency, and the structure mass, and the spreadsheet spits out how much fuel you need, how big the tanks must be, how many launches it would take to lift all of that into orbit, and how much margin is left for life support, shielding, and everything else. Over and over, when you run those numbers with technology that is even remotely near-term, you hit the same wall. High-speed trajectories are dominated by fuel. The mass for safety systems, shielding, redundancy, and comfort gets squeezed in, and the design stops making sense for a crewed mission. That's why, for now, most realistic human Mars plans stay in that 6 to 9 month per leg zone and accept a 2.5 to 3 year total. It's the region where the rocket equation hasn't completely turned the vehicle into a flying fuel depot. But even if you solve all of that propulsion and mass drama, you still have another timeline running in parallel, your own body's clock, because every extra day you spend on that long transfer, or waiting on Mars, demands oxygen, water, food, and reliable life support. And those systems also add mass and complexity. So how does stretching or shrinking the mission length collide with the basics of keeping a small group of humans alive away from Earth with what they can carry? If you strip away the rockets and the orbits for a second and just ask, how long can a small group of people stay alive away from Earth with what they can carry, the whole Mars timeline suddenly feels even heavier, because now every extra day on that 2.5 to 3 year mission turns into hard kilograms of stuff you need to launch. Start with basic daily numbers.
One person needs roughly 0.8 to 1 kilogram of oxygen per day just to breathe, around 2 to 3 kilograms of water per day to drink and rehydrate food, more if you count hygiene, and something like zero point 0.6 to 1 kilogram of dry food per day. So if you round that, you're at 4 to 5 kilograms per person per day. That's roughly 9 to 11 pounds, and that's before you talk about packaging, plastic, storage tanks, or any safety margin. Now, scale that to a real mission duration. Most conjunction-class Mars studies land around 900 days or more door-to-door, so let's just use 900 as a clean reference. Take 5 kilograms per day, 4 people, 900 days. That's 5 times 4 times 900. You end up at 18,000 kilograms. 18 metric tons of consumables if nothing is recycled. That's just oxygen, water, and food for 4 humans. No tools, no spare parts, no science gear. Just the basics to not die. In imperial terms, you're talking about something like 40,000 pounds of life support consumables alone.
That number is why everyone obsesses over recycling, because hauling 18 tons of one-way consumables all the way to Mars and back is insane from a launch perspective. But there's another angle. That mass has to be protected, stored, managed, and kept from spoiling or leaking for years, which means more containers, more structure, more monitoring hardware, all of which also add mass. The longer the mission, the more this pile grows, and the harder it becomes to fit inside any realistic launch stack. So you try to change the math. You don't want an open loop where you throw everything away after one use. You want a closed loop system as much as possible. The International Space Station is the current testbed for that. Up there, water is recycled with efficiencies above 90%. They reclaim moisture from the air, even from exhaled breath and sweat. They use systems to scrub carbon dioxide out of the air and split water to make oxygen again. That means you don't need to launch 900 days worth of fresh water and O2 as separate single-use cargo. But that fix comes with its own cost. Closed-loop hardware is not magic. It has mass. It needs power, it needs pumps, filters, spinning parts, chemical cartridges, control electronics, backup units, and it needs to run reliably for years without Earthside maintenance. On the ISS, if something in the life support chain fails, you can send a cargo ship with spare parts in a few months, and in a real emergency, you can return the crew in hours. On a Mars mission, when you are 200 million kilometers away, about 120 million miles, there is no emergency resupply. If your main water recycler or CO2 scrubber fails and you don't have enough redundancy, that can be mission ending. So every time you say, "we'll just recycle," you are shifting the problem. You are trading consumable mass for hardware mass and complexity. And you're betting heavily on reliability over a multi-year window, which is something we have much less direct experience with. Long ISS missions are months, not 3-year expeditions involving deep space, Mars gravity, and then more deep space on the way back. Now look at how mission duration hits you from both sides. Longer missions obviously need more food. Even with good recycling of water and oxygen, you still have to bring calories in some form. Maybe partially from stored dry food, maybe partially from plants grown on board. But the total needs scale with time. You also need more spare parts for everything. More filters, more replacement components for pumps, fans, sensors, and more backup systems in case a main unit fails halfway through. Every extra month on the mission adds to that reserve list. You can even put a rough number on how ugly that scaling gets. If you keep that 5 kilograms per person per day as a benchmark and run it for 4 people over 30 days, that is 5 times 4 times 30, so about 600 kilograms per month, more than half a ton. And again, that's before packaging and hardware. Each extra month you add to the timeline for the same crew size and recycling level is hundreds of kilograms of extra mass. Multiply that by dozens of months on a 3-year mission, and you see why designers are very sensitive about schedule creep. That is one of the reasons shorter transit times are so attractive, not just because astronauts want to get it over with, but because each month you cut from cruise time is 1 month less of high radiation exposure and also 1 month less of consumables and spares you need for that phase.
If propulsion technology lets you compress a leg from 8 months to 4 or 5, you can trim the stack of food, medical supplies, and spare parts you must assign to that leg, which directly shrinks the mass you need to push out of Earth's gravity. But you can't go crazy in the other direction either. If you demand very short trip times with today's or near-term engines, you push the rocket equation into the red zone and end up with a ship that is mostly propellant and almost no room for robust life support. So you're stuck balancing three things at once. The more conservative your propulsion is, the slower your mission, the heavier your life support needs, and the more redundancy you must build in. The more aggressive your propulsion is, the more you fight fuel mass and heating, and the less residual capacity you have for high comfort, highly redundant biological systems. This is why the how long to Mars and back question is really a three-way compromise. First, physics. You have orbits and delta V thresholds that set how much speed you need and when you can actually leave. Second, engineering. You have real engines with finite efficiency and real structures with finite strength. And third, biology. You have human bodies that need a stable environment, steady supplies, and systems that fail gracefully. You can push one side a bit, but the other two will push back hard. If you try to save mass by cutting life support margins too thin, you risk a situation where one failure cascades into a disaster because you can't resupply or repair. If you try to save money and complexity by accepting very long missions with slow transfers, you blow up the mass of consumables and the load on every system, including the crew. If you try to save time with extreme high-energy trajectories, you fight the rocket equation and may squeeze life support capacity out of the design entirely. And even if you somehow got the logistics perfect, and your recyclers never failed and your food never spoiled, there's another clock you cannot switch off: the radiation environment in deep space. Every extra day you spend coasting between planets, even with flawless water recycling and food planning, is another day of high-energy particles hammering your crew's bodies. So the next layer of this problem is not just can you feed people for 3 years, it's can their cells take the constant radiation hit for that long without pushing health risks into unacceptable territory. Even if you solve the rocket math and the life support logistics, there's still a timer running that you can't see. How long can your body sit in deep space radiation before the risk becomes unacceptable? Because once you leave Earth's magnetic field, the radiation environment changes completely. Out there, you're dealing with two main sources: galaxy cosmic rays, which are high-energy particles coming from outside the solar system, always there, all the time, and solar energetic particles, which are bursts from the sun, tied to solar flares and coronal mass ejections. The key point is you're not protected by Earth's magnetic field anymore. You only have your spacecraft walls and whatever shielding you brought. We have real data on this, not just theory. Instruments like the RAD detector on the Mars Science Laboratory cruise to Mars measured dose rates during interplanetary flight. They found something in the ballpark of about 0.5 to 0.7 millisieverts per day. Let's take 0.6 millisieverts per day as a rough, simple number. That's the sort of daily dose you'd be looking at in deep space, outside major solar storms with typical current shielding. Now run that forward over time, because radiation damage is about accumulated dose, not just single hits. At 0.6 millisieverts per day, after 200 days of cruise, you're sitting around 120 millisieverts total. After 600 days, you're around 360 millisieverts. That's just from the interplanetary legs, before you count anything you get on the surface of Mars or in low Earth orbit before and after. For comparison, a single abdominal CT scan might give you on the order of 10 to 20 millisieverts, so a multi-year Mars mission can stack up the equivalent of dozens of CT scans spread out over time. That kind of dose is not instantly deadly, but it is not nothing either. It increases your long-term risk of cancer and can have other biological effects. And remember, this is an average day-to-day estimate. It does not include a big solar particle event hitting you head-on, which can spike the dose significantly over hours. That's why missions will have storm shelters inside the spacecraft, thickened areas where the crew can hide during a solar event, using extra material or water tanks as a shield. Space agencies set career radiation limits for astronauts. They don't want one mission to burn through the entire lifetime safe budget. The exact numbers depend on the agency, the astronaut's age, but they are often in the range of a few hundred millisieverts, up to around 1 sievert as a lifetime cap. It's not a hard wall where 1.01 SV kills you, it's a risk management number. Beyond that, the extra probability of cancer and other effects is considered too high to justify for a career. A single conjunction class Mars mission with something like 7 to 9 months out, 500 days on Mars, 7 to 9 months back, plus margins, can easily take you into the range where you've used a large chunk of that allowed lifetime dose in one shot, especially if you are unlucky with solar activity. That's one reason agencies think very carefully about who they send, how old they are, and how many deep space missions a person can realistically fly. So how do you fight this? The main lever you have is shielding. You can put more material between the crew and the radiation. Water is good for this, so are plastics like polyethylene. And on Mars, once you land, you can cover habitats with regolith, the local soil, to cut down the dose from cosmic rays. On the surface, the thin atmosphere and the planet itself give you some protection compared to deep space. Not as good as Earth, but better than nothing. But shielding is heavy, and that's the same problem we keep coming back to. Every extra centimeter of material that you wrap around a habitat adds mass. If you cover a whole crew module with a thicker layer of water tanks or polyethylene, you're talking about tons of extra weight. And all of that has to be launched into space first. That is delta V you have to pay for before you even start the Mars leg. Once again, mass fights against mission design. The more you try to shield, the more your rocket equation budget gets squeezed. So you can't just say, we'll solve radiation by adding more shielding, without breaking something else. In practice, designers blend several strategies, some shielding from structure and water, some smart placement of storage around crew areas, some operational planning to avoid the worst solar conditions if possible, and storm shelters, where the crew can retreat for a few hours or days during bad events. But the background galactic cosmic rays are always there, and they're hard to stop without very thick, very heavy shielding. This is where travel time becomes more than just an engineering annoyance. Radiation risk scales roughly with how long you sit in deep space. The dose per day is mostly fixed by the environment and your shield design. So if you want to cut total dose, the cleanest way is to cut the number of days you expose the crew. That's a direct argument for shorter cruise times. If you can go from 250 days one way to, say, 120 days with better propulsion, you almost half the deep space dose for that leg, without changing shielding at all. That's why you see mission concepts where nuclear thermal propulsion or other advanced engines are pushed not only for schedule reasons, but also for health reasons. If you can cut both interplanetary legs from 8 to 9 months to 3 to 4 months, you're shaving many hundreds of millisieverts off the potential dose, which might mean the difference between a mission that uses up most of an astronaut's career limit and one that leaves room for future flights. Of course, you can't simply demand 3-month transits and ignore the rocket equation. Faster propulsion has to be physically and economically achievable. But as technology improves, radiation pushes you in the same direction that human comfort and logistics do. Everything points toward reducing time in deep space, as long as the required fuel and hardware remain within reach. Even if you manage that, and even if you get shielding and storm shelters right, radiation is only one part of the biological hit your body takes. The other big piece is gravity, or the lack of it. Because you're not just soaking up radiation for months, you're also floating in microgravity, losing bone and muscle, and then stepping into Mars's weaker gravity before going back to weightlessness again. So how long you stay away from Earth is also a direct question about how much physical degradation you can tolerate and still function as a planetary explorer. What good is getting to Mars faster if by the time you arrive, your body can't actually work on the surface? That's the quiet problem under all the timelines. Microgravity is running its own countdown on you the entire time you're floating between planets. In orbit, with almost no gravity, your skeleton and your muscles are basically unemployed. They don't have to hold you up. They don't have to fight 1G all day. And the body responds by quietly shutting things down. Astronauts in microgravity can lose around 1 to 2% of bone mass per month in weight-bearing areas, like the hips and spine, even with exercise. On a 6-month ISS stay, that is already a real, measurable loss. On a Mars mission that might last 30 months door to door, that isn't just a medical footnote, it becomes mission defining. Now, picture your timeline. 7 to 9 months in microgravity outbound, then you hit 0.38 G and live there for something like 500 days, then you go back into another 6 to 9 months in microgravity on the way back, and finally you hit 1 G again on Earth. That's 3 different gravity environments in one multi-year loop, each one pulling your body in a different direction, and you don't get to pause the mission every time your balance system or your heart is confused. So the obvious next question is, can we cheat this with artificial gravity? Could we spin the habitat to create a kind of fake gravity and keep your bones and muscles loading normally? In principle, yes. If you rotate a spacecraft, you can create a force that feels like gravity at the rim of that rotating section. But to make that feel comfortable and not make everyone sick, you need a large enough radius and the right spin rate. That implies big, complex structures, long arms or ring habitats, robust bearings, and the ability to control spin and vibration over years. All of that adds mass and mechanical complexity. If you build a big rotating section, you now have to launch and assemble more hardware in orbit. You have to deal with stresses from rotation, docking with a spinning structure, and what happens if your bearing system fails halfway through the mission? So while artificial gravity is often on the table in concept studies, it's not a simple plug-and-play solution. It's another heavy engineering-intensive system you have to justify against the already tight mass and risk budget. Right now, the main tool we have is exercise. On the ISS, astronauts spend about 2 to 3 hours per day doing physical training. They use treadmills with harnesses that pull them toward the belt, cycle ergometers, and resistance machines that simulate weightlifting. This is not for fun. It's strictly to slow down bone and muscle loss, not to stop it completely. And that's for missions that are typically 6 months, with some crew doing close to a year. Scale that to a Mars mission, and you're dedicating serious volume, mass, and power just to keep the crew from degrading too much. You need exercise machines that can operate reliably for years, spares for parts that will wear out, and enough space in the habitat for people to use them safely while also sharing that space as a living area. Those machines and spare parts are not light. They compete with other hardware in the mass budget. But cutting them is not an option if you want people to arrive on Mars able to work instead of barely able to stand. So microgravity and partial gravity turn into another driver for schedule. The longer you're away from 1G, the higher the risk of long-term health effects, like permanent bone density loss, cardiovascular changes, and neurological issues. And the more likely it is that crew performance will suffer exactly when you need them most, during high-stakes phases like landing, surface operations, and ascent. That pushes mission planners, again, towards shorter total mission durations, if propulsion and budgets allow. You start to see the pattern. Radiation and microgravity both point in the same direction. Every extra month in deep space or in a low-gravity environment makes the mission harder on the crew and demands more mitigation hardware, which raises mass, which feeds back into propulsion requirements, which pushes you back toward longer, more efficient transfers if you can't afford the fuel. It's a tight loop between health, hardware, and trajectory. And even if you accept that you need to keep the mission as short as the physics and rockets will realistically allow, you still cannot escape one big chunk of time that isn't about engines or health. It's about the orbits again, because Mars simply doesn't let you land, take a quick look around, and leave. The geometry forces you into a long stay if you want a low-energy ride home. So the next thing to understand is why you are stuck on Mars for so many hundreds of days once you get there, and why just plant the flag and come back is not a real option. If getting there and surviving the trip are this hard, why on top of that are you forced to sit on Mars for more than a year? Why can't you just land, do a quick mission, and leave on the next ship home, like a lunar mission scaled up? The core reason is simple and nasty. The same orbital geometry that gives you a cheap ride to Mars also locks when you can leave Mars again. In a conjunction class mission, which is the standard serious option for early human flights, the pattern is always the same. You leave Earth when Mars is ahead of Earth in its orbit by just the right angle. You follow a Hohmann-like transfer and arrive about 6 to 9 months later, and then you wait on the surface until Earth and Mars move into another favorable alignment for the return. That wait is not a small pause. For most conjunction-class designs, the surface stay comes out in the range of about 450 to 550 days, roughly 1.2 to 1.5 Earth years. That number is not chosen for convenience. It drops out of the orbital periods and the synodic period. In other words, from how long it takes the Earth-Mars system to rotate back into another efficient phase angle after your arrival. If you want a low-energy ride home, that's when you can go, not sooner. You might ask, can't we choose a mission that lets us leave earlier, even if it costs a bit more fuel? That's exactly what an opposition-class mission tries to do. In an opposition-class profile, you leave Earth when the alignment is such that you reach Mars, stay for a much shorter time, maybe a few tens of days, then depart again while Earth is on the opposite side of the Sun at some point in the cycle. The idea is to cut down the surface stay and sometimes the calendar time on Mars itself. But the cost shows up immediately. Those shorter stays often mean higher energy burns for both the outbound and the return legs. The trajectories may involve going inside Earth's orbit towards the Sun or using Venus assists. You can end up with longer total time in deep space, not shorter. And you spend more of that time far from both Earth and Mars, where abort options are basically zero, and the radiation environment is at its worst. So you trade time on a planet with some gravity and some shielding for time in the absolute worst place to be, empty interplanetary space. That is the central trade. Conjunction class, longer total mission, long surface stay, less time in deep space, and lower energy demands. Opposition class, shorter Mars surface time, potentially longer or more dangerous flight profile, higher delta V, more severe radiation, and abort problems. For a first generation of crewed missions, most serious studies bias toward conjunction class because it keeps more of the mission time either near a planet or in lower energy orbits, even though the surface stay looks intimidatingly long. If you look at actual numbers from mission architecture studies over the past decades, you see a pattern. You get designs with short stay profiles where the surface stay might be on the order of 30 days, a month or so, and long stay profiles where the surface stays around 500 days. Those 30-day solutions almost always come with a price, much higher total delta V, meaning more propellant, and more time in high radiation space. They usually push propellant fractions and mass budget into ranges that are painful for real rockets, while also making health and abort issues worse. In contrast, those long-stay options match more naturally with conjunction class. They share the pain between surface and cruise more evenly. You pay with a year plus on Mars, but you keep interplanetary legs in that 6 to 9 month band and don't demand extreme propulsion. For the same crew safety philosophy and similar technology, those long-stay options tend to sit in a more realistic zone, which is why they keep coming back in proposals, even though they sound excessive when you first hear them. From a human perspective, once you accept you're stuck there that long, you might as well use it. If you were spending billions, risking people's lives, and using up a big chunk of their radiation and microgravity budget in one mission, a 30-day flag planting run is a terrible deal. A 500-day stay lets you do serious science. You can run extended sample collection campaigns, drill meters down to look for past habitability signs, build climate records, test subsurface ice, and deploy long-term experiments that need many seasons of data. On top of that, a long stay lets you start building infrastructure instead of treating Mars as a one-off target. You can assemble and test more robust surface habitats, verify power systems to do different seasons, experiment with growing food under Martian conditions, and most importantly, test and scale in situ resource utilization, using Martian CO2 or water ice to make oxygen, fuel, or construction materials. These are the things you need if you ever want later missions to be cheaper, safer, or even permanently based there. So the long layover, which looks like a drawback when you see it in a table, is actually the only setup where you get enough time to stress test all the systems you need for future missions. That doesn't mean it's easy. A 500-day stay means 500 days of dust storms, hardware wear, crew stress, and potential failures far from any help. But if you're already forced to wait by orbital dynamics, smart mission design turns that dead time into productive time instead of treating Mars like a quick tourist stop. The important headline is this: long Mars stays are not some optional extra that planners bolted on for fun. They are baked in by the way Earth and Mars move, by the energy limits of realistic propulsion, and by the mass and risk penalties of trying to leave early. When someone says, why not just go, plant a flag, and come back in a few weeks, the honest answer is because the orbits will not give you a cheap, safe path home on that schedule. The real pattern is, if you go, you stay for more than a year, then you come back when the geometry finally cooperates again. And all of that waiting, all of that careful alignment and long surface work funnels into two brutally short episodes that decide whether the mission lives or dies. The minutes when you slam into Mars's thin atmosphere and try to land, and the minutes when you light the ascent vehicle and try to claw your way back into orbit. So after all these years of planning around windows and health limits, everything still hangs on a few critical events that are over in less than an hour each. You spend years planning, you spend months in deep space, and then everything comes down to a few minutes. Are you actually going to make it onto Mars in one piece, or do you turn years of work into a crater and a cloud of dust? Entry, descent, and landing on Mars is brutally short compared to the rest of the mission. You hit the atmosphere fast, something like 5 to 7 kilometers per second, around 11,000 to 15,000 miles per hour. And from that point, the clock is ticking. You have a few hundred seconds to get from hypervelocity fireball to standing on the surface with the vehicle intact. You slam into the air. You let the atmosphere start to slow you down, you deploy a heat shield, you ride the shockwave, then at the right time you throw out supersonic parachutes. And for heavy landers, you very likely finish with engines, retro rockets, or some kind of powered descent system. For a robotic rover like Curiosity or Perseverance, this whole thing took about 7 minutes from first atmospheric contact to touchdown. For a larger human-class vehicle, the exact times and speeds will differ, but we are still talking on the order of a few minutes to maybe 10 or 15 minutes from the top of the atmosphere to the ground. All of your months of transfer, all of the orbital mechanics, all of the life support design, and in this one short EDL sequence. And every parameter in that sequence depends on two things you set much earlier: your arrival speed and your vehicle mass. That is where Mars's atmosphere turns into a weird opponent. At the surface, the atmospheric pressure is less than 1% of Earth's, so the air is very thin. That gives you a nasty combination. It's too thin for parachutes alone to slow down a very heavy human lander all the way to a soft landing, but it is still thick enough to generate serious heating and complicated hypersonic aerodynamics at the top of the entry. So you get the worst of both worlds: strong heating and complex airflow when you hit the atmosphere, and then not enough drag deeper down to finish the job without rockets. On Earth, big capsules can come in, ride the thick air, deploy parachutes, maybe use a small set of retro rockets at the end. On Mars, for large mass, that won't cut it. The air just doesn't give you enough braking at reasonable parachute sizes. So you end up with designs that mix big heat shields, high temperature materials, advanced parachutes, and serious powered descent. All of that scales with mass, and remember, a human lander is much heavier than a 1-ton rover. You're talking tens of tons, including habitat, supplies, and ascent systems, so the design challenge jumps sharply. Once you're on the surface, the timeline stretches again. You don't just pop the hatch and go for a walk. The first days are about stabilizing the situation. You need to activate the habitat,
confirm that life support is working, check that all landed cargo survived and is accessible, inspect your power systems, whether they are solar, nuclear, or a mix, and survey the landing site for any hazards. That is the "are we safe" phase. Everything from leaks to misaligned antennas has to be caught and corrected early. Then you move into weeks and months of operations. Now it's about exploration sorties, driving rovers, collecting samples, drilling, setting up experiments, but also about infrastructure. You might be assembling additional habitat modules, deploying more solar arrays, burying parts of the habitat under regolith for radiation protection, and if the architecture uses it, starting up ISRU systems to produce oxygen or fuel from Martian CO2 or ice. Nothing ever works perfectly on the first try, so you need margin time to troubleshoot and repair. A 30-day touch and go leaves almost no room for serious science or fixing major faults, which is another reason short stays are not attractive in practice. Eventually, after hundreds of days, you have to leave, and Mars does not make that easy either. Getting off the surface is its own high-stakes, short-duration event. Your Mars ascent vehicle needs to reach something like 4 to 5 kilometers of orbital velocity, around 9,000 to 11,000 miles per hour, to get into Mars orbit and rendezvous with the return stage or the main ship. You dock, transfer crew and any valuable samples, then discard or park the ascent vehicle and prepare for the trans-Earth injection burn. Again, those burns are minutes long, but they are driven by everything that came before: how much fuel you managed to get into orbit, how accurate your ascent was, and how much mass your ship is carrying home. This is why these tiny slices of time, EDL and ascent, dominate so much of the design, even though they cover minutes out of a multi-year mission. They set hard limits on things like maximum arrival speed, maximum landed mass, how much molybdenum you need on the surface, and how much structure and shielding you need to protect the crew and the vehicle. Those limits feed directly back into the mass you have to push out of Earth's gravity well, which then locks in what kind of trajectory and transfer time you can actually afford. In other words, your 6 to 9 month cruises, your 500-day stay, and your total 2.5 to 3 year mission are wrapped around a handful of events that last less than an hour each. But those events are so demanding that they shape everything else. If you try to arrive much faster to save time, your EDL problem gets harder, your heat shield gets heavier, and your allowed landed mass may shrink, which hurts your life support and ISRU capabilities. If you try to shrink the ascent system to save mass, you may cut safety margins or propellant reserves too far, putting the return at risk. And even if you get the EDL and ascent designs right, there's another long clock running in the background. Not for the crew's door-to-door mission, but for the hardware you need to send ahead of them, especially if you plan to make the return fuel on Mars instead of hauling it from Earth. Because that choice adds an entirely new timeline on top of your 3-year trip. The timeline of building your ride home on another planet before you ever climb into the rocket on Earth. If getting down to Mars safely is scary, the thing that should really make you stop is this. How do you make sure you actually have a ride home waiting for you? Because if you try to launch all the return fuel from Earth, the rocket equation basically laughs in your face. The trick almost every serious Mars architecture leans on is in situ resource utilization, ISRU, which just means use Mars to help fuel the mission. Instead of hauling all the propellant for the Mars ascent vehicle and maybe part of the trip home, you bring some key ingredients and some machines, and you manufacture most of what you need on the surface before the crew ever shows up. There are two main ways people talk about doing this. One is you bring hydrogen from Earth in relatively small mass, and you react it with carbon dioxide from the Martian atmosphere. Mars's air is mostly CO2. You run that through a chemical process called the Sabatier reaction. The result is methane and water. You then split the water to get more oxygen. Now you have methane and oxygen as propellants. Those are compatible with certain engine designs, and you've turned local air plus imported hydrogen into tons of return fuel. The other main path is to go after water ice on Mars. We know there's water locked in the ground at high latitudes and likely accessible deposits at mid-latitudes in some regions. If you can mine that ice, melt it, and split it into hydrogen and oxygen with electrolysis, you get a pure hydrogen-oxygen propellant mix, which is extremely good rocket fuel, high performance, but it demands more digging, more processing, and more power because you're moving solid material, not just sucking in air. Either way, the appeal is obvious. This approach can cut your launch mass from Earth dramatically. Instead of sending tens of tons of propellant all the way from the surface of Earth to the surface of Mars, you send a much smaller ISRU plant, some equipment, and maybe some hydrogen, and you let Mars do the rest. But notice what you just traded. You swapped launch mass for power, machinery, and most importantly, time. To see how time enters the picture, put some rough numbers on it. Imagine your Mars Ascent Vehicle, the MAV, plus any orbital operations it has to do, needs on the order of tens of tons of propellant, say 30 or 40 tons combined of fuel and oxidizer. Now suppose your ISRU plant, for one configuration, can make about 1 kilogram of oxygen per hour when it is running properly. That means in one day, 24 hours, you get 24 kilograms of oxygen. In a year, that's about 8.8 metric tons, roughly 19,000 pounds. So if you need something like 30 tons total, you're looking at multiple years of continuous operation at that rate, and that's before you fold in any inefficiencies, downtime, or the need to make methane or hydrogen as well. This is why most ISRU-based plans assume the plant runs for months to years before the crew arrives. You want those tanks mostly full and the system proven before you put people's lives on the line. One common architecture looks like this. First, you launch an unmanned cargo mission that carries the empty Mars Ascent Vehicle and the ISRU hardware. You deploy power systems, hook up the plant to the local atmosphere or to water sources, and you switch it on. Then you wait, not for weeks, for a large fraction of a Martian year, which is about 687 Earth days, while it slowly manufactures and stores propellant. During that time, you're monitoring it from Earth, checking production rates, checking tank levels, watching for failures. The point is simple. You do not launch the crew until you know, with high confidence, that the fuel for their ride home already exists on Mars, or at least that the system is well on track to finish filling the tanks. This stretches the whole program timeline. Maybe you start the cargo and ISRU Phase 1 in one launch window and only send humans in the next window, 26 months later, but it makes the actual crew mission much safer. All of this depends on power, because ISRU is basically a factory. You're running pumps, compressors, chemical reactors, heaters, freezers, electrolysis units that all need steady electricity. On Mars, you have two main candidates, solar and nuclear. Solar looks attractive at first, no fuel to bring, just panels. But Mars gets fewer watts per square meter than Earth, and you have to deal with dust accumulation and dust storms. Big storms can cut your power output drastically for days or weeks, so you either oversize your arrays and add big battery banks, or you accept downtime in production. Nuclear reactors, on the other hand, can provide constant power day and night, independent of dust or weather. A compact fission reactor can run for years with the fuel you launch from Earth. But reactors are heavy, they have their own shielding and safety requirements, and flying and landing nuclear units on another world is not trivial. Still, for reliable ISRU and surface operations through Martian winters and storms, small nuclears look very attractive in many studies. Whatever you pick, the power system's output directly affects how fast you can fill the return tanks. Low power means a slow trickle of propellant and the longer pre-crew phase. High power means faster production, but more mass and complexity for your power infrastructure. Again, you're trading time against mass and risk. If you want the program to move faster, you pay in launch mass and engineering difficulty.
This is why ISRU is a hidden time cost. When people say the crew will be gone for about 2.5 to 3 years, they're only talking about the door-to-door time from the moment the astronauts leave Earth to the moment they come back. The actual Mars program timeline, from the first cargo launch to the last crew return, is much longer. You might be operating hardware on Mars for a decade, with ISRU plants running for years before any human boots touch the ground, and possibly for years after to support later missions. So even if you keep the crew mission itself in that 2.5 to 3 year band, there is a whole scaffolding of earlier missions and long-running infrastructure behind it. You are not just planning one big shot, you are building a staggered chain. First, you prove you can land heavy cargo. Then, you prove you can produce and store propellant reliably on Mars. Then, you finally commit humans, knowing that the hardware they depend on has already been tested by time and distance. And while all of that is happening, there's another limit you have to live with. You can't call up the ISRU plant or the crew and talk to them in real time, because even light needs minutes to cross the gap between Earth and Mars. That delay might sound like a small detail, but it completely changes how you plan operations and emergencies. So the next piece of this puzzle is understanding how communication lag and autonomy twist the schedule and force the crew to act more like a ship's captain in the age of sail than a pilot talking to mission control every second.
You know what really breaks the idea that mission control will just save them if something goes wrong? It's the speed of light. The one thing you can't hack, no matter how good your hardware is. Radio signals move at about 300,000 kilometers per second, around 186,000 miles per second. That sounds instant to us on Earth, but on the scale of orbits, it is slow. At the closest reasonable approach between Earth and Mars, the one-way light time is still roughly 4 to 5 minutes. At the far end of their orbits, that stretches to roughly 20 to 24 minutes one way. So you're looking at up to 40 plus minutes between asking a question and getting an answer. That means even in the best case, there is a built-in lag of several minutes on every radio exchange. In the worst case, almost half an hour one way. If a crew member says, "We have a problem," mission control hears that long after it actually started, and whatever they say back arrives even later. You never, at any point in the mission, get real-time back and forth the way you do with the ISS. There is no live conversation while you're landing, no turn left now style instructions, only delayed guidance and pre-planned procedures. That kills the idea of flying things like a video game from Earth. You can't joystick a lander or a rover in real time. Even with today's robotic missions, controllers send up sequences of commands, wait for the robot to execute them, then wait again for the data to come back. For humans, it gets even more serious. In a Mars landing, everything is pre-programmed and handled by onboard systems. By the time anyone on Earth sees the first line of telemetry, the crew is already on the ground or already crashed. For any rapid emergency, the people on the ship and on the surface are on their own. So in a crewed Mars mission, ground control's role changes. They're not directing every second, they're more like a strategic partner. They send planning, procedures, and advice, but the crew has to handle critical decisions locally, with no one talking in their ear in real time. That means you need a very different kind of training. You're not just training them to follow instructions, you're training them to be their own mission control when they have to be. And that shifts a lot of work forward into the pre-launch timeline. The delay also stretches every operation that does involve Earth. Say you're on Mars, a system starts acting weird. You diagnose what you can, then you package logs and sensor data and send them home. Earth gets that 10, 15, 20 minutes later. Engineers analyze it, maybe they need an hour, maybe they need a day. They send back a plan, another long delay before you receive it. That troubleshooting loop is naturally slow. You can't iterate fast with a 30 or 40-minute round trip baked in. So every task that depends on back and forth with the ground takes longer in calendar time. To make that workable, you push more autonomy into the hardware and the procedures. Vehicles need to make more decisions on their own. Software has to handle fault detection and recovery without waiting for humans on Earth to step in. Checklists and emergency playbooks have to be complete and executable by the crew without needing clarification for each step. That autonomy is not free. It increases software complexity, it increases the amount of testing you have to do on the ground, and it increases the training load on the crew. All of that is time spent before launch, months to years of simulation and debugging, so that when the radio lag is 20 minutes, the system doesn't stall waiting for permission. This delay also hits the human side in a way that's easy to underestimate. Think about what it means socially. Every call with family is shifted. You say something, they hear it much later, their reply comes much later again. There's no casual chat, no quick emotional feedback. Everything is more like sending voicemail back and forth with a long built-in pause. Over a multi-year mission, that can feel isolating. Even purely operational conversations feel slow. If you're used to real-time support on the ISS, where you can talk to flight controllers instantly, Mars feels like being back in the age of long-distance letters. You send a problem, you wait, you get a response, you wait, over and over. That delay adds a psychological weight to every decision, and it increases the sense that you and your small crew are alone. That affects stress levels, group dynamics, and long-term mental health, which you have to plan for in your mission design and crew selection. Because everything is so lagged and autonomy heavy, agencies don't want to run lots of short, frantic missions back to back. Each Mars mission is a huge operational and psychological event, with complex software, deep training, and crews that have to run a lot on their own judgment. You don't spin that up and shut it down casually every year. It pushes you towards fewer, bigger missions where you pack in as many objectives as you can for each multi-year campaign. That lines up with all the other constraints we've talked about: launch windows every 26 months, 6 to 9 month transfers, 500-day surface stays, ISRU timelines, radiation and microgravity limits. None of this supports a quick series of small weekend on Mars style missions. The physics, the engineering, the biology, and even the communication delay all point to the same picture. Each mission is rare, heavy, slow to set up, and loaded with objectives, and each one eats 2 to 3 years of the crew's life. So at this point, you've seen all the pieces separately: the orbits, the transfers, the life support, the radiation, the gravity, the ISRU, the comms delay. The question now is, if you put them all together and design a plausible mission in the 2030s using advanced but believable tech, what does that entire timeline actually look like, from the first launch to the day the crew walks back onto Earth? And why does that final number keep landing stubbornly in the 2.5 to 3 year range? So after all of this, if you actually sat down in the 2030s and said, all right, let's fly a real mission, what would the calendar look like? Not in pieces, but as one continuous story you could actually live through. Picture this: you're using technology that is advanced but believable. No magic drives. You've got heavy lift chemical rockets that can throw big modules into Earth orbit, maybe a nuclear thermal stage for the deep space push if the program is brave and mature enough. In year 0, month 0 on your mission calendar, the first launches start. Huge boosters loft pieces of the Mars transfer vehicle, cargo modules, maybe an inflatable habitat, maybe the nuclear stage, into low Earth orbit or a staging orbit a bit higher. For the first few months, there is no crew in deep space, just hardware. From about month 0 to month 3 or 4, rockets keep flying, assembling the spine of the Mars ship, docking modules, loading propellant, checking power systems, linking communication antennas. Between month 6 and finally the crew launches, probably in a smaller capsule. They rendezvous with the already assembled interplanetary vehicle, move over, and start living on the ship while it's still in Earth's neighborhood. By around month 6, all the checkouts and simulations in actual space are done, and the departure window is opening. You're sitting in a high Earth orbit, you light the big engine, chemical or nuclear thermal, and you commit to the transfer. That burn might last tens of minutes, but when it's done, you've left Earth's gravity well for good. You're now on a roughly 7-month Hohmann-like path towards Mars. Months 6 through 13 are deep space cruise. You're doing maintenance, exercising, running experiments, and watching Earth shrink into a point behind you. Around month 13, you reach Mars.
The ship executes the entry, descent, and landing sequence you already know is unforgiving. You hit the atmosphere at several kilometers per second, ride the plasma, deploy parachutes, fire descent engines, and if everything goes right, you're on the surface with your habitat and cargo. Surface operations begin right there. Month 13 is day 1 on Mars for the human part of the story. From month 13 to about month 29, you're in the long middle act, roughly 500 days on the surface, about a year and a half. You adapt to 0.38 G, you expand and harden the base, you run science campaigns, you drive rovers farther and farther out, you drill into the ground, you test ISRU systems that are making oxygen, water, maybe methane. You're constantly checking the ascent vehicle and its tanks because you know that one day, far in the future, you'll depend on that stack to get off this planet. During that same span, Earth and Mars keep moving. The geometry slowly shifts towards a new alignment, one where a low-energy path back to Earth is possible again. By around month 29, the return window finally opens. You've loaded the ascent vehicle with propellant, you've stored your critical samples, you've powered down or handed off base systems to wait for the next mission, and then you go vertical. Your ascent burns for minutes. You reach Mars orbit with roughly 4 to 5 kilometers per second of new speed. You rendezvous with the return stage or the main ship, dock, and get ready for the trip home. The trans-Earth injection burn happens, and now you're back in the deep space cruise phase, months 39 through about 36, another 7 months of microgravity and cosmic radiation, this time moving from Mars's orbit towards Earth's. The systems have to last, the shielding has to protect, the crew has to hold together mentally and physically after already living through nearly 2.5 years of mission time. Then, around month 36, you finally hit Earth. You separate into a re-entry capsule, slam into the atmosphere at several kilometers per second, and if everything goes right again, parachutes and possibly retro rockets bring you down to the surface. Door to door, you're looking at roughly 36 months, about 3 years. That's the full arc. The distance you travel when you add up all the curves of your orbit around the sun is on the order of 1 to 2 billion kilometers, something like 600 million to 1.2 billion miles, depending on the exact path. That's not a straight line. It's the sum of Earth's motion, your transfer, Mars's motion, and then the whole thing reversed on the way back. The accumulated radiation dose for each astronaut without very heavy, very expensive shielding could easily be several hundred millisieverts across both legs plus the surface stay. Now, could you do better than 3 years if everything breaks your way? If you assume high-performance nuclear thermal propulsion, very tight mass discipline, and a slightly more aggressive trajectory, you might design something closer to a 2-year total. Maybe something like 6 months out, about 400 days on Mars, 6 months back, plus a little overhead. That's roughly 24 to 28 months instead of 36, but it relies on hardware that has to be developed, tested, and proven, and on a mission plan that doesn't leave a lot of slack for big problems. On the other hand, if you stick strictly to chemical propulsion, add generous safety margins, and accept that schedules slip, you can easily drift above 3 years total. Delays in launch, slightly longer transfers to ease energy constraints, operational extensions on Mars to deal with issues, all of that stretches the mission, and engineers are more likely to pad timelines than to cut them to the bone when human lives are on the line. So why can't you just say, let's be bold and finish it in a year? The answer is that a 1-year round trip is not just ambitious, it is fundamentally in a different category. To do that, you'd need very high efficiency, high thrust propulsion that is far beyond what we're ready to use. Engines that deliver huge delta V without turning the vehicle into a flying fuel tank. You'd probably be talking about fusion drive concepts, advanced nuclear electric drives, or beamed propulsion systems that are nowhere near human-rated reality. You'd also need extreme assumptions about life support and shielding, either incredibly effective, light, closed-loop systems that don't fail over a year of intense operation, or some way of shrugging off radiation doses that are currently considered too high. On top of that, you'd have less time margin on Mars to fix anything that breaks, because you'd be rushing to hit an early departure window. All of that pushes you out of near-term engineering and straight into science fiction, not because we will never get there, but because it's not what you would honestly tell people is realistic for the first generation of human Mars missions. So when you step back and ask, how long would it take to go to Mars and come back on a real mission with today's physics and engineering that we can reasonably see coming in the next few decades? The answer keeps coming back to the same band. Expect something like 2.5 to 3 years door to door. Not because anyone likes that number, but because every month in that timeline is set by orbits you can't move, engines you can actually build, radiation your body can barely tolerate, and life support systems that have to work every single day or you don't come home. Change any of those pillars in a serious way, invent engines that are truly more efficient, figure out light and reliable artificial gravity, create much better radiation shielding, revolutionize closed-loop life support, and the entire clock for interplanetary travel will shift. But until that happens, if you sign up for a Mars mission, you're not taking a long trip. You're committing to a multi-year segment of your life where everything is dictated by one brutal question. Can you hang on, technically and biologically, for the full time it takes to leave one world, touch another, and then claw your way back? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.